Hello and welcome to another episode of Physics Problem Solving. My name is Ian and I'll be taking you through this question from the 2023 E&M subject exam, the life cycle of a muon. I will give you a moment to pause and try the question for yourself, and after that I will be back. Welcome back. I hope you have taken an attempt at the problem. I have started off with some notes on the question and I'll also read aloud. So a gamma ray with energy 4 E gamma travels in the plus Z direction. It collides with another gamma ray with energy E gamma traveling in the opposite direction, resulting in the pair production of a muon and an antimuon. The pair production occurs at threshold in the center of mass frame. The final momentum of the muon is the same as the final momentum of the antimuon. The rest mass of the muon is m, and its lifetime in its rest frame is tau. So, taking a look, first thing I usually do is draw a diagram. We have our gamma rays, 4e gamma, moving to the right, which I will call the plus z hat direction. And we have E gamma moving in the minus Z hat direction. And then we have our two muons, which are produced over here. But this isn't actually complete. Since we know this extra energy of an angle does not exist because of the keywords at threshold. So I will redraw this to actually be a little bit more accurate to the scenario that's happening. We have mu minus and mu plus. And with that, I think we can begin the question. So looking at number 1, what energy E gamma is needed to produce the muon-antimuon pair? Our main concepts for this question is going to be the form momentum, which is E over C, and the momentum vector. And looking at the two frames that we exist in. So in the lab frame, we have the gamma ray with 4 E gamma over C and momentum for E gamma over C Z hat. Gamma rays are light. We have no mass, which gives us E squared equals P squared C squared, or momentum equals E over C. And then we have our other gamma ray, which is going to be E gamma over C, and this is going to be negative E gamma over C in the Z hat direction, or E gamma over C in the negative Z hat direction. So our total form momentum in the lab frame is going to be 5 E gamma over C, 3 E gamma over C in the Z hat direction. All right, moving on to the center of mass frame. After the fact, we have the energy of the muon, which is just going to be m times c. And since we're in the center mass frame, we determined earlier that these muons are moving together, so they have no relative momentum. We also determined that the muon and the antimuon have the same mass, so we'll have another mc and another zero vector for momentum. And this will give us 2mc. Perfect. The next important concept is going to be that the constant e squared minus p squared is constant no matter what frame you're in. So we're going to use that to equate these. So we have 5 e gamma over c, 3 e gamma over c z hat squared equals 2mc 0 vector squared. And since they're 4 momentums, they square a little bit differently. This is going to give us 25 e gamma over c squared. This is minus 9 e gamma over c squared. And this is going to be equal to 4mc squared. We can simplify this to be 16 e gamma over c squared equals 4mc squared. And again, we're solving for e gamma, finding that threshold energy. Gamma equals square root of 1/4. This is m squared c to the 4th, which will just give us 1/2 mc squared. And that is our final answer for number 1. Alrighty, I've cleaned up my board and I've saved our result from number 1. But let's take a look at number 2. What is the magnitude and direction of the muon's momentum in the lab frame? So we want p mu final. And we have the initial lab frame. This was calculated from the first part. It is 3 e gamma over c in the z hat direction. We have some other critical pieces of information. Momentum of the muon is the same as the final momentum of the anti-muon. So let's do p mu minus equals p mu plus. And I'm just going to denote that as p sub mu. But this means that our p lab final is 2 p sub mu. So we can then relate these two, because we have the initial and final, and we have conservation of a momentum. So we then have the momentum of the muon and the anti-muon, actually, is going to be 3/2 e gamma over c z hat. And we found e gamma in the first one, so this is going to end up being 3/4 mc z hat. And that is our final answer. On to number 3. What is the total energy of the muon in the lab frame? Again, we're going to use 4 momentum, so this is going to be E mu over C and momentum mu squared, and that is going to equal m squared C squared. Perfect. Let us expand this. We have E mu squared over c squared minus momentum mu squared equals m squared c squared. And from number 2, you can see we have momentum of mu. So let's plug that in, and I'm also going to rearrange the c squared. So we have E mu squared is going to equal, let me do that one, 3/4 mc, all of that is squared, times c squared, plus m squared c to the 4th. Hopefully we can see that we can pull out m squared c to the 4th, m squared c to the 4th, and this is then going to be 9 over 16 plus 1, and that will give us a nice 25 over 16 m squared c to the 4th. This is still equal to E mu squared, so we want to take the square root of everything and get our final answer of E mu is 5/4 mc squared. Perfect. Now we can take a look at number 4. What is the magnitude and direction of the muon's relative velocity beta in the lab frame? So it does give us this equation for beta, which is the velocity over the speed of light, but that's not very helpful. What we actually want to do is, in the equation sheet, we have momentum equals gamma mc beta, and we also have energy equals gamma mc squared. So if we take momentum over energy, we get gamma mc beta over gamma mc squared. Let's cancel out the mc, the gamma, and we get beta is also equal to momentum over energy times c. And from parts 2 and 3, up in the top right, we can plug all of those values in. So we have momentum is 3/4 mc times c in the z hat direction. Have energy is 5/4 mc squared. Our m's and c's will all cancel, so will our 4's. So our final answer is beta is 3/5 in the z hat direction. Last but not least, we have part 5. How far does the muon travel in the lab frame before it decays? Looking at the previously solved portion, we have beta, and that equals 3/5 in the z hat direction. Let me just make sure I have all my vectors. And we can use relativistic velocity, gamma. This is 1 over the square root of 1 minus beta squared. And this is going to give us 1 over the square root of 16 over 25, which is going to be equal to 5/4. We also have that the time in the lab frame is going to be time dilated by gamma, so it's just going to be tau times gamma, where tau is the lifetime of the muon, and this is going to be equal to 5/4 tau. Awesome. That isn't quite what the question was asking for, though. We actually need the distance, so x lab which is just going to be the velocity in the lab frame times the time in the lab frame. Where, using the sneaky fact that we have beta, which is V over C, so beta times C gives us our velocity. So this is going to be beta times C times tau lab. So we have 3/5 times C times 5/4 times tau. Our 5's cancel out, and our distance in the lab is going to be 3/4 C tau. And that's it.